All right, here we go. We're looking at how to move AI from predicting the next token to making truly rational decisions in high-stake environments like fraud detection. A little bit of history. Pascal and Fermat established logic of belief, the idea that uncertainty could be calculated rather than just felt. This transformed decision-making from subjective judgments into mathematical objects. Our goal is to apply the same transition to large language models. While the framework operates on probability, preference can be subjective. In risk, there's such thing as risk appetite, which influences decision-making. The core principle is simple. You cannot make rational decisions without a mechanism to weigh the potential outcomes. Currently, large language models are trained to be helpful and agreeable, but that often leads to narrative bias rather than mathematical rationality. We gotta get probabilities. Quick thing on just fraud, how that works. Usually, human analysts review fraud, largely operates on expertise, but when there's many signals, they're bound to attend to finite set of signals. This is a problem because fraud detection is about finding needle in the haystack. So attention here is really about the negative space of all the obvious things, and that's why it is extremely hard. For our problem, we're evaluating business credit card applications, and as you can imagine, applications come with a bunch of different data, and the challenge here is really not about the lack of data. It's really the scarcity of ground truth and often the speed at which the adversary moves, because it's a adversarial game. Worse, these signals often contain traps. For instance, VPN mediates geographic mismatch. If AI doesn't understand that causal link, it will fail. It will double count risk, it can undercount risk, many different kind of traps, and we can get very different results because of not understanding the causal structure. Now, to test this, we built a 5-stage pipeline using GPT 5.2, generating complete synthetic data. We built a knowledge graph, build different kind of scenarios across industries and complexities, created Bayesian networks with different structures and conditional probability table, finally doing ancestral sampling and coming up with actual observed variables, and finally creating dossiers based on all of that. And this is what humans see and what large language models sees. But in the end, we have all that artifact that's used to generate this, so we can evaluate not just the final result, but also the generative structure. Evaluation, we are evaluating both large language model prompt techniques and also multi-agent techniques, and lastly, some classifiers for comparison as well. To begin, just to explain our contribution here, agents come together, build a Bayesian network, they debate about the causal structure, but in the end, we actually use a tool to do the posterior calculation. Result is pretty good. It's actually really good compared to just ask a large language model, which comes out to be roughly 67% top. However, with this new approach, we are able to build an okay model and jump the accuracy up to 82%. Prediction improves based on current prompts, though you can see it's not like monotonically increasing. I think I already kind of know the reason why, and this is just like work I need to do to continue to iterate on the different levers here. I actually do want to iterate on also subgroup things. I realized the subgroup things has like a lot of levers, and playing with those produce very different outcomes. So that's like one area also I want to spend more time on as well. Just coming back to Bayesian network construction, besides just looking at label accuracy, it's also important to look at how it's performing when it comes to uncovering the Bayesian network that produces the data, because that's really about understanding the generative process. And the number here looks pretty good, but the problem is that there's sort of like an easy case that dominates most of the edges, which is the edge from fraud to all the other observable variables. I plan to remove that from the calculation and see really how good it is at identifying inter-observable variable edges. I don't think it's doing very well right now, and I kind of know like why. So I plan to do more iteration on improving that. That's where I'm at currently. Thank you for listening.